See? Zoom in, zoom out, and just follow me around, basically. Okay. Thanks. Of course, as you guys are taping the course, what matters? Does it matter where I am? Doesn't matter at all. No one wants to see me. What matters is what I write on the board, right? So let that be your guide. Okay, so let's talk about, oh man, I don't even know what the good title is for today. Oh, I know. Analytic geometry. Let's talk about. So mostly what we want to talk about here today is points and vectors and components. So first things first, let me introduce some notation. First of all, R is the set of real numbers. I assume you guys know this already, right? R2 is the set of pairs of real numbers. So it would be something like x comma y, such that x and y are real numbers. That means element of, if you didn't know already. Sorry, I'm using some scary set builder notation. I will use it from time to time. If you don't understand it, you can just ask. This bar means such that, so this is a pair, x comma y, such that x and y are real numbers, right? So geometrically, we identify this with a plane, all right? Now, we can also talk about R3. This is the set of ordered triples, x, y, z, such that x, y, and z are what? Real numbers, right? So these are the basic layers. And we'd like to understand these as much as we can. So let me just show you our typical pictures for each. R, well, I guess there's a picture we draw for R, right? When did you learn this? 4th grade or something? 3rd grade? 2nd grade? I don't know. Number line, right? There it is. Oh, it does go on and on, I suppose. There's R for you. Now R2, you can draw something like this. Here's X, here's Y, right? So the Cartesian plane. Now there right there is the content of analytic geometry. It's this idea that I can identify a plane with these sets of ordered pairs, with a set of ordered pairs, right? But there's a unique correspondence between this very abstract idea of a geometric plane and these pairs of real numbers. Now, maybe you haven't even really thought about it because it's so ubiquitous to what we do, right? You're like, well, what else would you do? Well, remember Euclid had these axioms and parallel lines and all that. There were no numbers in that, right? This idea of attaching numbers to points and using numbers to measure the distance along a line, that's a really big event in math history, and it's part of why you're learning calculus, right? Let's see here. And then R3, what's our picture for R3? Something like, well, here's my typical picture. There's different ways to draw this. Obviously, Stephen Wolfram doesn't believe in this because apparently you can't do it in Mathematica. Although that's one of the tasks we decided. Dr. Wang has spent his entire summer building things that should already be integrated into Mathematica but aren't. Sorry, my personal opinion. But anyway, I think Dr. Wang has done very good work in Mathematica this summer. I'll probably share some of that with you as we go on here. But so here's my typical picture of R3, right? And again, I'm making an identification of three-dimensional space with these triples of real numbers. And so that's a picture that tries to get that idea across, right? That's a representation of this idea. Of course, it's a two-dimensional picture, right? So any point in 2 dimensions, what does it look like here? You pick a point. So we can go A comma B, right? What does that mean? That means that we've gone A out this way, and we've gone B out this way, right? So we can also think, though, about something called a vector, right? What's a vector? Yeah.
Quantity with direction and magnitude.
Quantity with direction and magnitude. I think that'll work. Here, I would also say it's a directed line segment, like an arrow. So if I want to, I can also think of this point in terms of a vector from another given point. Well, what other given points in natural choice to think about here? Yeah, 0, 0. That's kind of our go-to. So we can also think of AB as this vector. And so if I want to emphasize I'm thinking of the vector rather than the point, I might say that this blue arrow is angle bracket AB. All right. But here's the thing. Before too long, we identify points and vectors. So, you know, this is really just for me a point of language in this course. Here I'm saying it's a vector. Here I'm saying it's a point. But in terms of objects, I could just as well set them equal, but the question for me is one of emphasis, right? So you can add vectors and points. Anyway, let me erase this so that no one has evidence of it. Oh, oops. Now, any vector, like this AB, you can build from fundamental vectors that go along the coordinate directions, right? So like here, I can build it from this guy, like that, right? And so this vector, I can call A x hat. I'll be a little more explicit about that in just a second here. And then the vertical one, like this, I can call B y hat. Now, x hat and y hat, these are so-called unit vectors, all right? In terms of explicit formulas, x hat is equal to 1, 0, and my y hat is equal to 0, 1. So when I write ax hat, what is that actually? Let me just do the whole calculation down here. So what we have is we've got AB, and so here's the way vector addition works. It works component-wise. So the definition of vector addition allows me to, it's easier to see kind of going, if you read this menu style, it's easier to understand. So menu style is like right to left. So if you try to understand, add this to that. How do you add vectors? You add the x component to the x component, the y component to the y component. I think I just introduced a new term, components, right? So if you add that to that and that to that, we get a plus 0, b plus 0, which is just ab. So this is an identity. But then scalar multiplication is so defined so that you equal a out here and equal b out there. Oops. And so there you have it, ax hat plus by hat. So any two-dimensional vector can be written as a linear combination of the x hat vector and the y hat vector. These are unit vectors. We will soon learn that those have length 1. All right, as soon as we introduce length. I'm going to define some things. I'm putting the cart before the horse here a little bit, and then I'm using some definitions I haven't stated yet. All right, so that's bad form, but I hope it makes more sense when we get to the end of it. Now, 3 dimensions, what's that look like? Oh, some more language before I get there. By hat is the so-called vector component of, let me give this thing a name. What do you want to call it?
Bob.
Bob? Okay. Did you say 2? That's so much worse. I like it. So if this is the Bob vector, this is the y vector component of Bob. This is the x vector component of Bob. What are the scalar components of Bob? A and B, right? A and B are numbers, whereas the vector components are vectors. You cannot write a vector as a sum of its scalar components because that's like apples and oranges. It doesn't make sense. Vectors must be added to vectors, right? So the vector components, ax hat and by hat, these are vectors. And the way I'm talking about addition is tip to tail, right? You notice this? So I take this vector plus that vector, that gives me the vector b. That actually is an example of the tip to tail vector addition right there. Let me keep on here. So in 3 dimensions, oops. To start with, I might just think about a point in 3-dimensional space, right? And I could call that ABC, for lack of imagination. And that point, obviously, you got to set up some coordinate axes, right? So whenever I'm in a room like this, thankfully we have rectangular rooms, almost always without exception. Oh, man! Oh, this is just a very thick coordinate axis. There you go, there's the z coordinate axis, that's just really. Soprano. Some weight behind it. All right, so this is the z-axis, and let's see here, as I'm imagining it, that would be the x-axis, and that would be the y-axis. All right, so Mr. Gibson there, for example, might be, let's see, I don't know, I guess I need to choose a system of units, but we use feet, I guess we're about, what, 10 feet out here, maybe about 15 feet that way, and I'm guessing to the top of your head, 3 feet. So the coordinates of top of Mr. Gibson's head there would be something like 10, I already forgot, 10, 15, 3. Right, you guys are kind of familiar with this idea, right? Okay, so, but you understand that there's a giant leap there to make this assumption that you can actually make a one-to-one identification with points in physical space in R3. R3 is a totally mathematical construction. Physical space, well, it's physical space, right? Before the fact, why should they be identified? I don't know, it took us like 2,000 years to realize that there was a question to be asked there though, so if you don't see what I'm saying right away, it's okay. You got some good company. Now, so obviously we can identify that with the directed line segment from the origin in 3 dimensions, right? So if I want to emphasize that it's a vector, I use my angle brackets. I got something like v is equal to abc, right? And again, I can decompose it into ax hat plus by hat plus cz hat. But this time, see, context matters, right? In this context, the x hat is what? 1, 0, 0, right? The y hat is 0, 1, 0. And the z hat, 0, 0, 1. So those are displacements in one unit of measure in the x, y, or z direction, respectively. And a very similar calculation shows that that equality is true, right? With respect to the vector addition I have not defined for you carefully yet. But you notice here, there's an extra 0, right? In the 3-dimensional context. Oh, so what does the picture look like? Something like this, right? So here's what I think. First thing I think about is like, what's its projection down to the xy plane? So its shadow, if you were looking directly down, is the projection onto the xy plane. So that point would be what? That would be a, b, 0. Basically, you just set the z component to be 0. And then you can think about like parallel to the y, like that, right? And you can think about also, and this is also, yeah, the dotted lines, maybe I should make them a different color, make them red. The red dotted lines are in the xy plane, okay? So just to emphasize geometrically what ax, so ax hat's like this. See that? Bx hat would be like, by hat rather, is this guy. And then finally, cz hat is this character right here. Again, this is a resolution of the vector v into its Cartesian vector components. What are the Cartesian scalar components here? ABC, right? We good? All right, so now that I've been using vector addition for like 10 minutes or whatever, let me actually bother to define it for you. Definition: if v and w are elements of Rn, then that means that v is equal to something like v1, v2, vn, and w is equal to w1, w2, wn. Then v plus w, the jth component of that, is defined to be what? While you're thinking, what's the scalar multiple of c times v also? Yeah, you looked at my notes and you cheated? Yes, I suppose we would. Wait a minute, I looked at my notes too. I can't hope to answer this. The answer is component-wise, right? So what you do is you just say it's Bj plus Wj, and here it's just C times Bj. That's how I actually did this, right? I added the first to the first to get the first. I added the second to the second to get the second. That's how you do it. Oh, and I also seem to have sneakily introduced the notion of Rn here. If you can do 2 and 3, you can just as well do 20, right? And why not define it for all at the same time, because it's just as much work. There's the definitions. So we can prove theorems with respect to this definition without a lot of trouble. But even if I never told you this definition, this is just what you guys would do. It's just natural to add vectors this way. Now, geometrically, why that's natural has to do with, on the geometric side of things, we could look at it like this. Here's A, right? I'll try to make B easy enough to think about like this, B. So geometrically in calculus 3, because we're working in Euclidean space, we can move vectors around by keeping their magnitude and direction the same, right? In other words, we can change their point of attachment. Like, of course, A here is attached to point P1, B is attached to point P2, but you notice I don't have any reflection of where they're attached in our basic notation. That's a blessing and a curse. It's a blessing because we don't have to say where they're attached. It's a curse because sometimes you really need to know where they're attached. It's very different for me to tell you there's a vector which points to a plane, as opposed to for me to tell you there's a vector which lies on a plane, or a vector which is tangent to a plane. A vector which is tangent to a plane means that the vector is actually along the plane. A vector which points to the plane could be like that, where the end of the vector is just pointing to the plane. I'm sorry, my arm's not a very good plane, but I bring it across. Sorry. So what's A plus B here? A plus B is C. Right. Well, to be lazy, what I'm going to do is I'm just going to move B over where I can add. So you do tip the tail, right? So let's move B over here. And so this guy down here is what we would call A plus B. That is 100% the same as this up here. You're like, well, how is that? Well, if you take these vectors and you break them into their Cartesian components, then you're just adding them, right? Like, look at this instead as like, here's my A, here's my, this is A2y hat, here's A1 x hat. B is actually equal to by hat. Oh, by hat. Sometimes we have an hour, right?
15 minutes.
Why did they change them to hour meetings? Sometimes it's Friday hour, right?
3:15 to 4:05.
Sure. Yeah, the other class didn't believe me either. Anyway, so you take any vector, right? You break it into its x and y pieces, and then you can move these things around and basically just stack all the y's together, and stack all the x's together. What's the length of the whole thing? Well, it's each piece in the y added together, it's each piece in the x added together. So that you could do geometrically, but that again reproduces these rules up here. So I mean, these are one and the same idea. The tip-to-tail idea and that formula. Okay, you guys would rather me talk about distance though. How do we understand distance in 2 and 3 dimensions? So I'm going to jump straight to the 3-dimensional case because, of course, and we're just going to talk about the distance to the origin because if we understand that, we can understand the distance between other points. It's like a trick. So what's the distance to this point, A, B, C? By the way, once we figure this out, shouldn't that be the same as the length of the vector ABC? Think about it. Is there one in the same problem? So what I do, it goes back to the picture I already drew over there. I just think about the projection of the point down in the xy plane, which gives me AB0, right? And then I've got two two-dimensional properties, right? On the one hand, I've got this triangle down here, which I'll shade, well, as much as you can shade anything on a whiteboard, where I've got side length A and side length B, right? But I've also got a vertical triangle, like this, right? It's also a right triangle. That's harder to see in my picture, but it's true. You can see it. What's the length of this down here?
Square root of A squared plus B squared.
Yeah. Do you guys see how we saw that? Because there's, I guess, different ways to look at it, but what I'm thinking about is this triangle in the xy plane, right? It's a right triangle, AB squared of A squared plus B squared is length of the hypotenuse. So the green line I'm about to draw has length what? Like when I haven't drawn it yet, so what am I supposed to tell you? And then I drew it C, right? So look at the red triangle. What's the length of this hypotenuse, right? Which I'll make more sense. What's that length?
Square root of A squared plus B squared plus C squared.
Right. Well, A squared plus, and I would say, just to put the thought process in here, oops, C squared. A squared plus B squared, squared, right? Which, as you guys already told me, the distance from ABC to the origin, right, that is the distance function, and it is equal to the square root of A squared plus B squared plus C squared. So this is D for distance. The distance between these 2 points is that. Now, that's also equal to what we call the vector length, or norm, the length of the vector ABC. So here, the double bars are to be understood as the length of a vector. That's what that notation is, okay? So, okay, well, I just told you if we can figure out this distance, we can figure out the distance between arbitrary points in R3. How do we do that? We use this vector, right? So like if I have a point P, and if I have a point Q, right? And I want to figure out what's the distance from P to Q, how should I do that? Yeah. Yeah, subtract the coordinates. So by the way, that, you can think of as a directed line segment actually, right? This would be what we would call, maybe you had a high school geometry course where you use PQ for that. That's the vector which goes from the point P to the point Q. And right, he's exactly right. If we take the difference of the points, that actually gives us a formula for that vector. It's Q minus P. Right? So if I want to calculate the distance from point P to point Q, all I do is I calculate the length of Q minus P. Which when you work out the details for specific 2 points, it's just like that 2-point distance formula you learned before with an extra thing added on. The difference between the z components squared. Oops, I forgot x, y, z. There are other, you could make this one be z if you wanted. If I made that one be z, then I gotta think about it though. Go, oh. Y. Yeah, x, I guess. Is that right? I'm sorry, I don't know what I was doing. I don't know about that yet. I was doing some crazy thing with my right hand just then. Don't accuse me of it. We'll soon not learn that. So, something else I wanted to say here. Any questions while I do that dangerous thing called thinking? No? Should get the clocks in here. Until 4:10, right? Oh, just one more comment, and then I really will stop. So tomorrow we'll talk about the dot product, which is so important. this little thing I did right here can be viewed in terms of vector addition. So, I think it's good to do that. Here's Q, here's P, right? So this is the vector Q, this is the vector P from the origin, right? So, what is, right here, I said we had PQ, right? So if you look at this Q vector plus PQ vector should be equal to what? I do this plus that should be the same as that. So that should be equal to P. And you see that's just what I claimed. The PQ was equal to P minus, oh man.
You switch the Q.
No! How do I do that? Goodness gracious. Fine. I think you can see how to take this and fix it.
You would have had it right, you just scaled the position.
I know, I set myself up to do the start of my picture. If any one of you noticed that when I drew that picture, didn't say something, it's on you. Anyway, that's all I got for today. I'll see you tomorrow. Thanks, guys. You press the button.